This is Free Range Digital Design Foundation Modeling, Chapter 22, second lecture. And this chapter is about registers, and a very important circuit that uses a register is an accumulator. So registers are everywhere in digital design. Accumulators are used quite often, and let's look at it. Now I'm just essentially going to plop the circuit diagram for an accumulator down here. I'm not going to derive it. I think it's something if you see one time you will always remember this thing. Okay, so generally speaking in digital design, typically you have to do something with a set of numbers or a list of numbers. For example, add them. Most circuits, all the circuits I've ever seen in digital design, they only do one operation at a time. That means they add two numbers at a time. So if you have a list of numbers to add, essentially you're going to add two of those numbers, then add the third number to the total of the first two numbers, etc., etc. So this is essentially an accumulate operation. Since I can only add one number at a time, I'm essentially keeping a running total of the numbers as I add them. So eventually when I get through the whole list, I will have the sum of the entire list. Now the issue here is these are done with a clock signal, which fits great with the registers because the register is synchronous based on the clock input. And other issue here is we really have to make sure we get the data widths designed correctly. So here's your circuit here. This is the input data, and this is the previous running total data here. Now the previous running total data is going to be stored in this register. It's going to be latched in that register with that clock signal there. Once again, I'm using this triangle for a clock signal. I'm not bothering drawing a clock. If you look at the circuit, the register is a sequential circuit, of course. The ripple carry adder is a combinatorial circuit. Typically what people often try to do is not use a register, and they connect that sum output to one of the input operands in the ripple carry adder, and that essentially creates a random number generator because it's simply adding in this loop as fast as you can, as fast as the hardware allows it. And so this has a name, and they call it a combinatorial loop, which is a common error in your HDL. If you have a combinatorial loop, that means you have something like a random number generator. You don't want to do that. So the issue here is you're getting the data in at a certain width, you're adding it together, so it makes sense that the output data needs to be at a different width, which is typically, of course, it's going to be a bigger width depending on how many pieces of data you're going to add. So the output width is this n here is going to depend on how many pieces of data you're going to add, or to put differently, it's going to depend on the maximum number that this register needs to hold. The issue is I'm going to be on the lookout for an accumulation function in any circuit that I design. When I see that, I'm going to plop these two circuits down very quickly and hook them up, and then worry about the widths later. Typically speaking, what I have to do is bit stuff or sign extend the input data to make it happy with the width of the accumulator, width of the register data for the ripple carry adder. So these are issues you always have to deal with in problems like this. So the data widths are important. You have to have the output data of the accumulator, the width of the output data, wide enough to handle whatever operation you're doing. Okay, so generally, if you can make it as big as you want, but the general theme of digital design is to make your circuits as minimal as possible and still get the job done. So you want to generally design these to be as minimal as possible and still work. The issue with the accumulator here is you're adding many numbers together, and it has to be able to handle the accumulation or the addition of numbers without issues. And the issues are going to be a carry out of that ripple carry adder for unsigned numbers, or it's just going to be general overflow for signed numbers. And typically, if you don't design it right, you're going to have to check for these things and react accordingly if you get one of these two error conditions. So as an example here, where we have a circuit that's going to accumulate 8 unsigned 10-bit values. Okay, so what's the width of the accumulator going to be on this one? And so that means 10-bit, that's 2 to the 10th, and I'm going to have 8 of those. That's 2 to the 3rd. So the maximum value is going to be 2 to the 3rd times 2 to the 10th, which if you remember your logarithm blah blah blah, it's going to be 2 to the 13th. So the answer here is the width of, if I'm going to accumulate 8 unsigned 10-bit values, I need that output to be 13 bits wide. This is a calculation typically you're going to have to do with every circuit that uses an accumulator. Typically the problems don't state the width of the accumulator. It's part of the problem where you have to calculate it yourself. This is the last final word on registers here, and what we have is, in this chapter, is simple registers, but later we'll come across 2 more very useful registers, which namely these counters and shift registers. Counter is another register. Both these have all the qualities of registers plus other features. A counter counts, of course, and a shift register shifts. These are topics for later chapters. Just want you to be aware of how popular registers are and useful they are in digital design. This circuit, this is a design problem, and I need to keep a running total of 8-bit unsigned binary inputs. This is a problem that actually states the width of the output, so I don't need to worry about that. There's another issue in this thing. So let's do this. It's a circuit. The width is 10 bits as stated by the problem. It has an input value of 8 bits, and we also have a clock signal coming into this thing, since it's going to be a synchronous circuit. So when I look at this problem, I immediately see that it says running total cries out for an accumulator. Without too much effort here, I'm going to draw that accumulator. I'm not going to draw the data widths on it. So there's a lot of work in that problem already. So the issue is it's adding, it quoted 10 bits on the output, and so I had to make that 10 bits. I didn't need to do a calculation. So that means the ripple carry outer associated with this accumulator is also 10 bits. Input's 8 bits, which means I have to stuff 2 bits there, and I put a little note there. There's my little bit stuffing symbol. Other issues on this, I have a clock input on the register. The clock input is not drawn. It's understood to be there because I have the triangle there. I have a load input. I decided to put that in there. I tied it to always load, and the problem stated no different, and we're almost done with this problem. The other thing we need to do in this problem is handle the fact when it carries out. So if there's a carry out of this ripple carry adder, what it says to do is I need to clear that register, which says the output resets. So the issue here is when I get a carry out, I need to magically put a clear input on this thing. I think I'm going to modify this a little bit. So when that generates a carry out, I'm connecting that carry out to the clear input. So when this carry out's asserted, it turns that clear input on, and I'll say clear. I didn't really need to put that, but I'll say it's also asynchronous. And I need to put that it's asynchronous on there. And essentially when this summation creates an overflow or a carry out from this ripple carry adder, it clears this register. It's an interesting problem. We'll be able to handle this a little bit more cleanly in other chapters when we have some better control elements here. So lastly in this thing is the issue of what's controlling it. We have a clear input here. This load is tied high. What connects to that clear input, which is a control input, is an internal signal. So this is, and I look this over, I'm going to look it over one more time, make sure I got everything labeled on this one, add that in there to help, and then I'm going to call it done. Okay, lastly, registers are foundation modules. Typically they have clear, load, and clock inputs, which are the control inputs. They always have a clock. Generally they have a load, and sometimes they have a clear. Once it has a clear, you need to state whether that clear is synchronous or asynchronous. Load is always assumed to be synchronous. Data coming in, data coming out, these data widths always match. If they don't match, you better have a good reason for them not to match.